Please attend Zoom lectures. I have more time to speak there than I do on these YouTube videos. This section are the 3 gas laws, the first of which is Boyle's, and notice it's from 1662. And it says that at constant temperature, that's the important point, a fixed gas occupies a volume that is inversely proportional to the pressure. This means there is a relationship, and I can replace that proportionality with an equal sign as a constant. This really looks like V is equal to K over P, and if I toss the P to the other side, I come up with that expression. You're going to be using it as P1. V1 equals P2 V2. Now that's the math. Here is the concept, and here it is in a graph form, all right? And what you want to notice is at a high volume, the pressure is very low, and at a low volume, the pressure is very high. Scientists like straight lines, so they're going to plot V versus 1 over P to get that gorgeous straight line. You'll be working on problems, and really, I'm going to tabulate it as if I was sitting in the classroom with you. I'm going to say P1 is equal to 1.2 atmospheres. I'm going to say V1 is equal to 1.2 liters. I'm going to say P2 is equal to 2.4 atmospheres, and I don't know what V2 is. Again, tabulate your information. What's the best formula to use? Well, we just did one. P1 V1 equals P2 V2. What we want to do is solve that expression for V2. V2 is going to equal P1 over P2 times V1. So I'm going to substitute my values in. P1 is 1.2 atmospheres. P2 is 2.4 atmospheres. And my volume is 1.2 liters. Notice how the units cancel, and we come up with the value 6.0 liters. Again, very simple problem. Any units are acceptable because they are going to be, as long as they are the same, they are going to cancel out. That's what my atmospheres did. Now, this is a very simple problem. It's just to illustrate the law. The second law is Charles' law. And again, look from when it was, 1787. And what it says is that the volume is directly proportional to temperature. So when I replace that proportionality with an equal and a K, I have that expression. If I solve for K, it's V over T. And if I set up a relationship between two systems, V1 over T1 is equal to V2 over T2. The important thing to note here is that my temperature must be in units of Kelvin. Where did that come from? Well, here is some data that someone plotted for volume versus temperature. No matter what gas they used, that gas always intersected the x-axis at minus 273 degrees centigrade. So we're able to use that relationship as long as we put in that factor. What will you be doing? Well, it's another type of problem. I'll let you read the verbiage because I want to spend my time talking about it. V1 is equal to 117 milliliters. V2 is equal to 234 milliliters. T1, well, it's equal to 100 degrees centigrade, but I need to turn it into Kelvin, so I'm going to add 273 and have 373 Kelvin. What is my V2? That's what they're asking here. So I have my relationship. V1 over T1 is equal to V2 over T2, and I am going to be solving for T2. So T2, just using the symbols, is V2 over V1 times T1. So let me put my numbers in. 234 mLs divided by 117 mLs times 373 Kelvin. That will give me a value of 746 Kelvin, but they're normally going to ask you for centigrade, 473 degrees centigrade. Again, I'll let you stop this video. I'll let you read it through. But notice, temperature must be in Kelvin, and you can have any units for volume as long as they are the same so that they cancel out. The last part of the gas law is Avogadro's law. Now, he came back up with the mole way back in chapter 3. He came up with this relationship in 1811. That's over 200 years ago. And what he said is that equal volumes of gases at the same temperature contain this, and pressure, I need to add that, contain the same number of molecules. So there is his proportionality. There is where he replaced it with an equal sign and it's K. So the thing to note about this is at the same volume, pressure, and temperature, if I have different gases, they have the same number of molecules. We had that back in chapter 3 when we talked about Avogadro's number. But what we noted is that each gas has a different mass. So that sometimes comes to you as a word problem. I didn't take my time with this. I'm going to take my time in the lecture Zoom, give you a couple more examples, but I want to get this posted so if you miss lecture Zoom, you have the information.